Welcome to Lesson 4 of my Red Pill course on calculus, where we will discuss the concept of uniform continuity. In Lesson 3, we introduced S-continuity as preserving infinite proximity. F is S-continuous at A if and only if f is a real function and A is in the domain of f, and for all x in the domain of f, if x is infinitely close to a, then f of x is infinitely close to f of a. If we look at the function graph through a magnifying glass with unlimited magnification, we can see an infinitesimal variation of the argument induces an infinitesimal variation of the function value. We then used standardization to derive the standard concept of pointwise continuity. Cont is defined as the standard subset of f cross R, whose standard members are those that satisfy S-cont. By definition of cont, for all standard Fa, f is continuous at A if and only if f is S-continuous at A. This is generally not correct for non-standard Fa. By transfer, we conclude a standard function is continuous everywhere if and only if it is S-continuous at each standard point of its domain. More generally, an internal, that is, conventional, parameter-dependent statement involving continuity is true for all parameter values if it is true for all standard values. We now look at S-continuity as a global concept. We say that a real function f is S-continuous if and only if it is S-continuous everywhere on its domain. That is, for all a in the domain of f, f is S-continuous at a. Or equivalently, for all x1, x2 in the domain of f, if x1 is infinitely close to x2, then f of x1 is infinitely close to f of x2. We can obtain a standard concept from S-continuity by standardization. We define ucont as the standard subset of f whose standard members are those that are S-continuous. The functions in ucont are called uniformly continuous. Compare this to the definition of continuity. We defined cont as the standard subset of f cross R whose standard members are those pairs Fa for which f is S-continuous at A. Thus, the standardization of pointwise S-continuity results in the standard concept of pointwise continuity. The standardization of global S-continuity results in the standard concept of uniform continuity. For any standard function f, the following statements are equivalent. F is uniformly continuous. F is S-continuous. For all x1, x2 in the domain of f, if x1 is infinitely close to x2, then f of x1 is infinitely close to f of x2. For any standard function f, the following statements are equivalent. F is continuous. F is S-continuous at each standard point of its domain. For any real function f, if f is uniformly continuous, then f is continuous. This is clear for all standard f by the above characterization. Then, by transfer, the implication holds for all f. The reverse implication is not generally true, but it is true in special cases, as we will see now. One important special case are continuous functions on closed bounded intervals. Let a, b be real numbers, a less than or equal to b, and f a continuous function on the closed interval from a to b. Then f is also uniformly continuous. For the proof, let a, b, f initially be standard, and f a continuous function on the closed interval from a to b. Let x1, x2 be in the interval ab and infinitely close. Then x1 is limited. Let x be its standard part. We have a less than or equal to x1, less than or equal to b. Taking standard parts yields a less than or equal to x less than or equal to b. That is, x is also in the domain of f. Since f is continuous, x is standard and x, x1, x2 are infinitely close, we conclude f of x1, f of x, f of x2 are infinitely close. Hence, f is uniformly continuous. The general case follows by transfer. We take a look at some examples. The function on R that maps x to x squared is standard. It is not S-continuous because it is not S-continuous at unlimited points. However, it is continuous because it is a standard function and S-continuous at all standard points. It is not uniformly continuous because it is a standard function but not S-continuous everywhere. If we restrict the function that maps x to x squared to the closed interval from 0 to 1, it is standard and S-continuous everywhere on its domain. Therefore, the function is continuous and uniformly continuous. If we restrict the function that maps x to x squared to the closed interval from 0 to u, where u is positive unlimited, then the function is not standard, and it is not S-continuous at unlimited points. Nevertheless, it is of course continuous, and as a continuous function on a closed bounded interval, it is also uniformly continuous. Finally, we consider the function on the closed interval from 0 to 1, which maps x to the n, where n is an unlimited natural number. This function is not standard and not S-continuous everywhere, for example, not at point 1, where an infinitesimal variation of the argument can induce a non-infinitesimal variation of the function value. Like every polynomial function, this function is continuous, and as a continuous function on a closed bounded interval, it is also uniformly continuous. An important property of continuous functions is expressed in the extreme value theorem. Let a, b be real numbers, a less than or equal to b, and f a continuous function on the closed interval from a to b. Then f attains a minimum and a maximum. In the figure, the minimum is attained at S1 and the maximum at S2. Of course, it is also possible that a function attains its minimum or maximum more than once. The proof we will give for the extreme value theorem is typical of non-standard analysis. The idea is to reduce the situation to a discrete finite problem. To this end, we divide the interval AB into a finite number of subintervals of equal length using the points x0 to xn. We now consider the function values at points x0 to xn. Since there are a finite number of values, there is a least and a greatest among them. The least value is first attained at some point xi1 and the greatest value at some point xi2. If the interval is divided finely enough, we can expect the function to attain a minimum near xi1 and a maximum near xi2. We refine this idea by considering the standard case and assuming an unlimited number n of subintervals. As usual, the general case then follows by transfer. So let A, B, F initially be standard. Let n be an unlimited natural number. For I from 0 to n, we define an equidistant partition of the interval AB by the points xi, which are equal to A plus I times the interval length b minus a divided by n. We define yi as the respective function values of the points xi. Let I1 and I2 be the lowest indices such that each yi is between yi1 and yi2. Since a and b are standard, all xi are limited and their standard parts exist. Let S1 be the standard part of xi1 and S2 the standard part of xi2. xi1 is between a and b, and by taking the standard parts, we deduce that S1 is between a and b. Analogously, we deduce that S2 is between a and b. Since f and S1 are standard and f is continuous, f of S1 is infinitely close to f of xi1, which is equal to yi1. Hence, f of S1 is the standard part of yi1. Analogously, f of S2 is the standard part of yi2. Let x be a standard real in the interval AB. There is some I such that x is between xi and xi plus 1, and therefore infinitely close to xi. Since f is continuous and standard, f of x is infinitely close to f of xi, which is equal to yi. Hence, f of x is the standard part of yi. Taking standard parts here in the inequality marked in yellow yields f of S1 is less than or equal to f of x, which is less than or equal to f of S2. This is true for all standard x in the interval AB, hence by transfer for all x in the interval AB. This means that f attains a minimum at S1 and a maximum at S2. For general ABF, the assertion follows by transfer. Let's summarize the most important results of this lesson. The concept of uniform continuity results from the standardization of global S-continuity. Uniformly continuous functions are continuous. Continuous functions on closed bounded intervals are also uniformly continuous and attain a minimum and a maximum. We will close with a somewhat generalized way of speaking. For a real function f and a subset D of its domain, we say that f is uniformly continuous on D if the restriction of f to D is uniformly continuous. The theorems discussed in this lesson then apply accordingly. That means, for example, that a continuous function whose domain contains a closed bounded interval is uniformly continuous on this interval, and that the restriction of the function to this interval attains a minimum and a maximum. The next lesson is dedicated to differential calculus. I look forward to welcoming you there.